All right, in this video, we're going to talk about section 2.2, which is describing sets. And out of this section, we're going to be applying set language and structure to elementary mathematics. Also, we'll explain connections between finite sets and whole numbers and determine whether sets can be placed in a one-to-one correspondence. Okay, now, set theory was created by George Cantor. And this concept has a profound effect on research and mathematical thinking. Sets and relations between sets are a basis for teaching children the concept of whole number and the concept of less than, as well as addition, subtraction, and multiplication of whole numbers. All right, now to begin this section, we need to learn some definitions here. So we'll start off with the language of sets, right? A set is going to be any group of collection of objects, okay? So in this example here, you see this is a set A. It's just a collection of objects, and the objects that belong to a set are the elements, or what we call the members of a set. So in this set, the members are 1, 2, 3, 4, and 5. And one method of denoting a set is to simply list the elements inside the braces and label the set with a capital letter. So here, this set has elements inside the braces, and then you have a capital letter. In this case, it's capital letter A, so we can call this set A. Okay. Also, each element of a set is listed only once. And then the order of the elements is unimportant. So the order here can be anything we want to. We can list the elements of set A as 5, 4, 3, 2, and 1. So the order does not matter. We symbolize that an element belongs to a set by using this symbol. It looks like an E, but that symbol represents that the element belongs to a set. And if an element does not belong to a set, here we use that symbol where we have a slash over the E to indicate that an element does not belong to the set. Also, a set must be well defined. That means we must be able to tell whether or not an object belongs to the set. Okay. All right. Now, there are methods of describing sets. One of them is the listing method, or sometimes it's called the roster method. Okay. So in this case here, we have set C representing the colors red, green, yellow, and blue. And then we got set N, which is a set of natural numbers. And that set is listed as 1, 2, 3, 4. And then we got 3 dots right behind it. Those are called ellipses, which means that this set continues in the same manner. It continues on and on without end. And then the capital letter L, that represents a set of lowercase numbers like A, B, C, D, and so on with 3 dots or the ellipses behind it. Okay. Also, we have set builder notation as another method of describing sets. All right, so this is what set builder notation looks like. And the way we read something that's in set builder notation would be this. Set C is equal to the set of all numbers or all elements X. This vertical bar is read such that, and then we read this off. X is an element of the set of natural numbers, and X is less than 5. Okay, that's the way we read something that's written in set builder notation. Okay. Now, here's a couple of examples of taking the set that's where we use the listing method and write it in set builder notation. Like in this case here, we want to use the set builder notation to write the following sets whose elements are the terms of an arithmetic sequence. Like for this one, A is equal to the elements 2, 4, 6, 8, 10, and so on. So if I wanted to write that in set builder notation, we can look at this as the set of even numbers, because that's what we have here, 2, 4, 6, 8, 10, and so on. So in set builder notation, we can write like this. It's going to be the set with the left parentheses of all x, such that x is equal to, let's say, 2 times n, because in this case, as you can see, even numbers are just going to be the number multiplied by 2. And we need to define what n is. N is going to be an element of the natural numbers. Okay. And in example B, you'll see 1, 3, 5, 7, those elements, and it goes on and on and on. Well, those are odd numbers, as you can see. So that means here, if we want to write that in set builder notation, it could be this set of all x, such that x is equal to, let's say, 2n minus 1, because it's going to be 2 times whatever n is, and then we subtract 1. Okay, because 2n is going to be even. To make it odd, we subtract 1. Okay, so here, of course, n is the element of the natural numbers. Okay, so that's how we can write something like this in set builder notation. Now, let's look at another example where we have this in set builder notation, and we want to write the set A, which is the elements, which is a set of all 2k plus 1, such that k is equal to 3, 4, and 5. And we want to use the listing method. Well, let's think about this. We got k is equal to 3, k is equal to 4, and k is equal to 5. If I want to use a listing method, pretty much I have to substitute each k with each of these values here. So if k is equal to 3, this will be 2 times k, which is going to be replaced with the 3, plus 1. Now 2 times 3 will be 6. 6 plus 1 is 7. And then for k is equal to 4, this will be 2 times k, which is 4, plus 1. That would be 8 plus 1, which is 9. And then for k is equal to 5, this will be 2 times 5 plus 1. 2 times 5 will be 10. 10 plus 1 is 11. So using the listing method, this set builder notation will just be 7, have the elements 7, 9, and 11. That's all there is to it. Okay. All right. Let's say we had this. Let's say I want to write this set. And in this case here, B is going to be the set of all x such that x is a positive, even natural number less than 8. A positive, even natural number less than 8. So in this case, set B would look like this. Okay, it's a natural number, so that means if it starts from 1, 2, 3, 4 up to infinity. And then your even numbers will be 2, 4, and we have to stop at 6. We can't list 8 because 8 is not less than itself. So only 2, 4, and 6 would be the set of all x such that x is a positive even number less than 8. And here we're using the listing method for that. Okay. All right. Now let's define equal sets. All right. Two sets are equal if and only if they contain the same elements. Okay. So with equal sets, the order of the elements makes no difference. And if set A is equal to set B, then we can write that as just this: A is equal to B. And if A is equal to B, then every element of set A is contained in set B, and every element of set B is contained in set A. And then for A is not equal to B, what that means is that there is at least one element that is not contained in both sets A and B. Okay, now, to further explain this, let's take a look at this homework example, which is similar to one of the problems in the MyMathLab homework. So here, we want to identify which of the following sets are equal. Okay, and these are the ones that are given to you. And here we're going to select all of those, the ones that apply. Okay, equal sets means that you must have the exact elements in one set as you do in the other. And if you look at this, here's set A and here's set C. It has D, F, J, K, and the other one is J, K, F, D. The order is different, but they do have the exact same elements in A as you do in C. And you have the exact same elements in C as you do in A. So A equals C. That's one possibility. Now, what about C equaling to D? In this case here, C and D are not, because D in this case is going to be this. X is between 3 and 6, and that does include 3 and 6. So that's like 3, 4, 5, and 6 for set D. And as you can see here, C has just lowercase letters, but D has numbers in it. So C can't be equal to D. What about E equaling to H? Okay, take a look at E and H. Here's E, which is the empty set. H is also the empty set as well. These are just two different notations for the empty set. The circle with the slash over it, and also just the braces with nothing in it. Those two are notations for the empty set. So E equal to H is the other pair of sets that's equal. What about J equal to L? Here's J and here's L. This represents where n is a whole number, 5n plus 5, which is equal to x for all x. The other one, 5n minus 5 for every natural number. Now, whole numbers, which is the W, start off with 0. So for J, here's what we have here. 0 times 5 plus 5 will be 5. 1 times 5 will be 5 plus 5 will be 10. 5 times 2 is 10 plus 5 will be 15, and so on. And then for L, natural numbers, of course, we talked about that. It starts with 1, 2, 3, 4, and so on. So if we do 5n minus 5, this will be 5 times 1, which is 5, minus 5 is 0. Automatically, I can see that 0 is not an element in J. So J and L will not be equal. Let's see, what about E and F? Let's look at E and look at F. These two are different. E represents the empty set, F does not. That means even though you have a circle with a slash for the empty set, it's inside the braces. That means that there is something inside that set. And then finally, A is equal to B. That's false right here because A and B have letters that are different from each other. So the only two sets that are equal would be A is equal to C and E is equal to H. For them to be equal, you must have the same, every element in A must be in B, and every element in B must be in A. All right, here's another homework example. You'll want to find out which of the following sets are equal. Well, let's look at J equaling to L. Here's J, and here's L. Whole numbers start with 0. So if I was to write this, that would mean, let's say 3 times 0 is 0. 3 times 1 would be 3. 3 times 2, which is 6. 3 times 3, which is 9, and so on. The n, which is your natural number, starts with 1. And this is for x equal 3n minus 5. So this will be like 3 times 1, which is 3 minus 5, which is negative 2. Well, already J and L can't be equal because here negative 2 would not be in J. Let's look at A and B. Well, notice A and B are not equal because of the different letters that I have in in A as I do in B. What about D equaling to L? All right, here's D, and that's L. Notice that D is just simply between 1 and 3, including your endpoints 1 and 3. And notice that in L, negative 2 is there, but in D, negative 2 is not. So we can leave that out. All right, and what about J equaling to K? Well, look at K and look at J. Not the same. Every element in K is not in J. So that's out. What about A and C? It is. Because here's A and here's C. BFJ and JFB, the order is different, but they are the same. They do have the same elements in C as you do in A, and you have the same elements in A as you do in C. And C is equal to D. No. C has lowercase letters, D has just numbers. Okay, so A equal to C is the only pair of sets that are equal to each other. Okay. All right, next we'll look at one-to-one correspondence. One-to-one correspondence. And it says here, if the elements of sets P and S can be paired so that for each element of P, there is exactly one element of S, and for each element of S, there is exactly one element of P, then the two sets P and S are said to be in a one-to-one correspondence. So in this case here, sets 1, 2, and 3 can be placed in a one-to-one correspondence with set A, B, and C by establishing either of the following pairings, like this one. I can pair the 1 with the A, the 2 with the B, and 3 with C. And if I wrote these set of numbers as 3, 2, and 1, that means 3 can be paired with A, 2 can be paired with B, and 1 can be paired with C. So you would have a one-to-one correspondence. Now, these are not only the possible pairs to establish a one-to-one correspondence. Let's say we want to list all the possibilities. And you'll see that on the next page. Okay. So here's one way to illustrate all the possible one-to-one correspondences, and that is to use a table, and the other is going to be using a tree. So here you can see that there are 6 possible one-to-one correspondences, where 1 can be paired with A, 2 can be paired with B, 3 can be paired with C. And then another A, 1 with A, 2 with C, and 3 with B. Or 1 with B, 2 with A, 3 with C. And then 1 with B, 2 with C, 3 with A. Or 1 with C, 2 with A, 3 with B. And then finally 1 with C, 2 with B, 3 with A. Okay. And here's the factor tree, the tree right here, A, B, and C. So the first number could be A, B, or C. And if I choose A, then the second would be either B or C. The third can be a C with A and B. And then with A and C, I can pair that with B, and so on. So here there are 6 possibilities for a one-to-one correspondence. Okay. Now, excuse me. How can we determine the number of one-to-one correspondences between 2 sets? Now, if we, in that example that we just looked at, given the element 1, the first set, there are 3 possible elements in the second set which can be paired with 1, namely A, B, and C. And once we paired an element with 1, that leaves 2 elements in the second set to pair with the number 2. And once we paired an element in the second set with 1 and 2, then you'll be left with only 1 element left in the second set to pair with 3. Okay. So now in this homework example number 3, we want to find out which of the following pairs of sets can be placed in a one-to-one correspondence. Well, take a look at part A. You got 1, 2, 3, 4, and MNAT. Notice I have 4 elements in this first set and 4 elements in the second set. So here, this can be placed in a one-to-one correspondence. So I'll just answer that as yes. Now, in the homework, they might give you that as a answer choice to answer yes or no, like in this case right here. So for each one, you just answer yes or no. All right, now in part B, we got A, B, C, D, and so on up to C, and 1, 2, 3, all the way up to 26. We should know that in the alphabet, there are 26 letters in the alphabet. And there are 26 numbers up from 1 to 26. Well, that can be put into a one-to-one correspondence here. So this is also yes. Now let's look at part C, the set of all T's such that T is a letter in the word pulp, and the set 1, 2, 3, 4. Well, this set is going to end up being the empty set because the letter T is not in the word pulp. and then you got 1, 2, 3, 4. You have nothing in this set to pair with the numbers 1, 2, 3, and 4. So this cannot be placed in a one-to-one correspondence. So that would be no for that answer for part C. Okay. All right, let's look at another homework example. Let's say we want to determine which pairs can be placed in a one-to-one correspondence, like, of course, 1, 2, 3, 4, 5, and MNODT. We have 5 numbers here and 5 letters here that can be placed in a one-to-one correspondence. So here, that answer there would be yes. Now, part B, we got ABC all the way up to F, and then 5, 10, 15 up to 25. If I was to write this out, ABC all the way up to F would be A, B, C, D, E, and F. And then 5, 10, 15 up to 25, those are multiples of 5. So this would be 5, 10, 15, 20, 25. I can pair the A with the 5, the B with 10, C with 15, D with 20, and E with 25, but I have nothing to pair with that F. So that means this cannot be put in a one-to-one correspondence. So the answer to part B would be no. Now part C, the set of all T such that T is the letter in the word jar and the numbers 1, 2, 3, 4. Well, this set has to be the empty set because the word jar does not have the letter T in it. And I have nothing in that set to pair with these numbers 1, 2, 3, 4. So obviously that cannot be put in a one-to-one correspondence. Okay. Okay. So that's how we determine whether pairs of sets can be placed in a one-to-one correspondence. All right, next we'll look at the fundamental counting principle. The fundamental counting principle. If event M can occur M ways, and after it has occurred, event N can occur N number of ways, then event M followed by event N can occur M times N ways. So basically all you're going to do there is just multiply the number of ways that event M occurs by the number of ways event N can occur. For example, Colin's Pizza House offers 3 kinds of salad, 15 kinds of pizza, and 4 kinds of dessert. How many different 3-course meals consisting of a salad, pizza, and dessert can be made? Okay. Now this fundamental counting principle works for more than 2 ways or more than 2 events. So here, 3 kinds of salad, that would be 3, times 15 kinds of pizza, that's 15, times 4 desserts. So we're just going to multiply 3 times 15 times 4. And that would give us 180. So there's 180 ways of creating a 3-course meal that consists of a salad, pizza, and dessert. Okay. All right, now we'll talk about equivalent sets. Equivalent sets. In this case, there are 2 sets, A and B. 2 sets, A and B, are equivalent, which is written like this: A with a squiggly mark and then B. A is equivalent to B if there is a one-to-one correspondence between the sets. Now, if you remember that if two sets are equal, they have the same elements, meaning A is equal to B, the elements in A must be exactly the same as the elements in B. Also, equal sets are equivalent, but equivalent sets are not necessarily going to be equal. Okay? Because equivalent sets, I can come up with a one-to-one correspondence. Equal sets means what's in A has to be in B, and what's in B has to be in A. So in this case right here, let's say we let A be a set with the elements P, Q, R, S. B has the elements A, B, C has the elements X, Y, Z, and D has the elements B, A, C. And here I want to compare those sets using the terms equal and equivalent. Well, if you think about this, each set is both equivalent and equal to itself. In other words, A is equal to A, B is equal to B, C is equal to C, D is equal to D. They're equal to themselves, and also they're equivalent. A is equivalent to A, B is equivalent to B, C is equivalent to itself, and D is equivalent to itself as well. Because I can come up with one-to-one correspondences for each one. Now, sets A and B are not equivalent and not equal. Here's A and here's B. As you can see, they're not equal because A and B have different elements here. And here, they're not equivalent because I'm not able to come up with a one-to-one correspondence for A and B. Also, sets A and C are not equivalent and not equal for the same reasons, because I can't come up with a one-to-one correspondence with A and C. And also, the elements that are in A are not in C, and the elements in C are not in A. Now, sets A and D, if I compare those two, they're not equivalent and not equal for the same reason. What's in D is not in A, and what's in A is not in D. And I can't come up with a one-to-one correspondence with those two sets, A and D. Now, sets B and C, they're equivalent because I can come up with a one-to-one correspondence. But they're not equal because what's in B is not in C, and what's in C is not in A. All right, take a look at B and D, sets B and D. They are equivalent because I can come up with a one-to-one correspondence, and they are equal because what's in D is also in B, and what's in B is also in D. Now compare set C and D. They're equivalent. Unfortunately, they're not equal. They're equivalent because I can come up with a one-to-one correspondence with set C and D, but not equal because what's in D is not in C, and what's in C is not in D. Okay. Okay. Now let's look at another definition, and that is cardinal numbers. In this case, the cardinal number of a set called S is going to be denoted by this notation, N with the capital letter S in parentheses. That's going to be the number of elements in set S. So if we wanted to find the cardinality of each of the following, like K is equal to 3, 5, 8, 0, and 11, there are 5 elements in set K. So that means the number of elements in set K would be equal to 5. And then L has the element 0. There's only one element there, so that means the number of elements in L would be 1. Now for set X, which is in set builder notation, a set about X such that X is a real number and X is equal to X plus 1. Notice the number of elements in X is going to be 0. The reason for that is this. Now work this out to the side. X is equal to X plus 1. If I try to solve this equation for X by subtracting X on both sides, so I can get all the X's on one side, what's going to happen here is these X's are gone. I'm left with 0. And on the right side of the equation, those X's are gone. I'm left with 1. 0 equals to 1 is a false statement. So the equation X equal to X plus 1 has no solution. So that means the number of elements in set X will be 0. And look at set Y, has the equal set. By definition, the empty set is a set with no elements in them. So the number of elements in set Y will be 0. Okay. All right, let's talk about the difference between finite sets and infinite sets. A set is finite if its cardinality is 0 or a natural number. A couple of examples would be the set of presidents in the United States. Okay, and right now, as of the date of this video, there are 46 presidents in the United States that we've had. So that's a finite set. Also, the set of planets in our solar system, there are 9 planets in the solar system. So that's a finite set. Now, if we don't have a finite set, that means we have an infinite set. Usually an infinite set is going to be a set that has the 3 dots or the ellipsis, meaning it goes on and on and on forever without end. Like for the set of whole numbers, which we write out as 0, 1, 2, 3, and so on. And then the set of solutions to the equation X plus 1 is equal to X plus 1. If you try to solve this equation for X, and then you try to get all the X's on one side by subtracting X on both sides, these X's are gone, you're left with 1. And on the right side, those X's are gone, you're left with 1. So in this case here, 1 does equal to 1. And when that happens, that means that there are infinitely many solutions here. Any X value that you pick, the left side will always equal to the right side. So that set would be an infinite set. All right. Here's some more things that are related to sets. All right, in this case here, the universal set or the universe denoted by a capital letter U is going to be the set of all elements being considered in a given discussion. So let's say we have the universal set defined as this. U is equal to the set of all X such that X is a member of the United States Senate. That would be considered a universal set. That's going to be a set of all elements considered in a given discussion. Denote the universal set with a large rectangle, and particular sets are indicated by geometric figures inside the rectangle. In this case, only members of the United States Senate are included in the rectangle. And this pictorial representation is what we call a Venn diagram, which you'll see on the next page of your handout. So this is what a Venn diagram looks like. The universal set would be that rectangle. And inside the rectangle, we'll have circles representing a well-defined set. So if we consider the members of the universal set, which is U, who are females. Since this set is wholly contained in U, but does not contain all the members of U, we denote this set with a circle as follows. So here, capital F, that's going to be the set of all X, such that X is a female United States senator. Okay. All right, let's take a look at the next homework example that I have. Here you're going to draw a Venn diagram showing the relationship between the set of natural numbers and the set of whole numbers. And we want to choose the correct Venn diagram. So the relationship between the set of natural numbers and the set of whole numbers. Well, whole numbers consist of 0, 1, 2, 3, 4, and so on. Natural numbers consist of just 1, 2, 3, 4. So the outer circle represents a set of whole numbers. The inner circle represents all the natural numbers. Okay. So it has to be this answer choice right here. Okay, because it can't be B and it cannot be C right here. Okay, because all the natural numbers are whole numbers. But not necessarily all the whole numbers natural numbers. Reason for that is whole numbers contain 0. The natural numbers does not. It starts off as 1. Okay. All right, the next thing is the complement of a set. The complement of a set. Consider the members of the universal set, which is U, who are not females. This is the set of all members of the set U that are not in F. So we refer to this as the complement of set F and denote it by a shaded region in the figure below. Well, here's the set builder notation, the set of all F equaling to the set of all X, such that X is a female U.S. senator. But on the next page, you'll see that shaded region where the individual is not a female U.S. senator, okay? Because F represents the elements of a female U.S. senator. If they're not a female U.S. senator, it will be this set on the outside that's shaded in green. So let's formally define a set complement. The complement of a set called A is going to be written as A with a bar on top. That's going to be the set of all elements in the universal set U that are not in A. That is, in set builder notation, a complement, and some textbooks will call it, is the set of all X, such that X is an element of the universal set and X is not an element in set A. All right, so let's look at these few examples here dealing with the set complement. Let's start up with part A. If U has the elements A, B, C, and D, which is the universal set, and B has the elements C and D, find the complement of B, the complement of U, and the complement of the empty set. Okay. So in this case here, if B has the element C, D, that means we take away any elements here that's also in the universal set. So if we take away the C and the D, because those elements are in set B, you're going to be left with these two elements, A and B. So the complement of B would be the set A, B. The complement of the set U, which is a universal set, well, here's a universal set, A, B, C, D. Its complement means you just take all of these numbers out. They're gone. All you'll be left with is the empty set. And of course, the complement of the empty set, or the complement of the empty set, well, if the empty set has no elements in it, then its complement will have to be the entire universal set. Has to be. And you can think of this, the empty set has nothing in it. And you compare that with the universal set. Take nothing from the universal set, it will be the universal set. All right, in this next example, if U, the universal set, is a set of all X such that X is an animal in the zoo, and S is a set of all X such that X is a snake in the zoo, describe S complement. In this case, the way you just have to write this in words is going to have to be this. The set of all X such that X is an animal that is not a snake. Because if you take out all the snake animals that are snakes, you'll be left with the remaining animals that are not snakes. Okay. And part C, if the universal set is a set of natural numbers, which is N, E has the elements 2, 4, 6, 8, and so on, and O has the elements 1, 3, 5, 7, and so on. I want the complement of E and the complement of O. In this case, if you take away E complement, the even numbers, if you take those even numbers away from the universal set, which is the set of all natural numbers, guess what you'll be left with? The set of odd numbers, which is, of course, defined as O. I'm sorry, we don't need this on top. It's just a set of odd numbers, O. And O complement, if you take away the set of odd numbers from the universal set, you'll be left with just a set of even numbers, E. Okay. All right, now let's look at another definition called subsets and the notation for that. Here, set B is a subset of A, written like this. B is a subset of A, if and only if every element of B is an element of A. And when a set A is not a subset of another set B, we write it like this. We use this symbol with a slash over it to indicate that set A is not a subset of B. Okay. Now, what's the difference between subsets and equality of sets? Here, the definition allows for B to be equal to A. And that's where you have this underscore underneath that symbol. B is an element of A, or B, well, not element, B is a subset of A. Here, B is a subset of A, which is what that means. And that's if and only if every element of B is an element of A. And of course, if A is a subset of B and B is a subset of A, then that means that A is equal to B. A is equal to B. Now, how do we define a proper subset? How do we define a proper subset? Let's say that set B is a subset of A, and B is not equal to A. What that means here is this: that must be at least one element of A that is not in B. And that's illustrated in this diagram, the Venn diagram. Is a universal set. And then here, B, of course, is a subset of A. The problem with that is it's not going to be equal to A, because this dot represents an element in A that is not in B. So we say here that B is a proper subset of A, and we write that as using this symbol without that equal sign underneath it. So B would be considered a proper subset of A, because there is at least one element that's in A that is not in B. Okay. So let's look at this example. Let's say we are given that A has these elements 1, 2, 3, 4, and 5. B has the elements 1 and 3. And P is a set of all x such that x is equal to 2 to the n minus 1, where n is an element of the natural numbers. Okay. So here I want to identify all the subset relationships that occur among these sets. Okay. Now in this case here, let's say 2 to the 1 is, 2 to the 1 minus 1. That's going to be coming from P being the element, the set of all x such that x is equal to 2 to the n minus 1. So 2 to the 1 is 2, minus 1 will be 1. For n is 2, 2 squared minus 1. That's 4 minus 1, which will be 3. And I keep going on and on and on. That would mean P will have to be 1, 3. And let's carry this out a bit. N is 3, this will be 8. 2 to the third is 8 minus 1, which will be 7. And for n is 4, 2 to the fourth is 8 minus 1, which is 15, and so on. So we can see here, if we compare that, B is an element of, it's a subset of P. B is a subset of P because all the elements that are in set B are in set P. And also something else, we can see that B is a subset of A, and also A is a subset of itself, A. B is also a subset of itself, B. And then P is a subset of P, of itself. So as you can see here, these are all of the subset relationships that occur among A, B, and P. And then part B is to identify all proper subset relationships that occur among those sets. Well, in this case here, B is a proper subset of A because what's in A is also not in B. The elements in set A are not in B. So B is a proper subset of A. Also, B is a proper subset of P. Because if you take a look at this, all the elements that are in P are not in B. Okay. All right, now let's look at a homework example. Indicate which symbol is an element of or is not an element of, is an element of or not an element of, makes each of the following statements true. 0 and the empty set. Keep in mind the empty set has nothing in it. So 0 can't be in that empty set. So we have to say 0 is not an element of the empty set. Part B, 8,193 in this set, the set of all x such that x is equal to 2 to the nth power, where n is a set of the natural numbers. Well, I know 2 to the nth power, and n can be any natural number. That x is going to be an even number. Look at 8,193. That's odd. That's an odd number. So that means here, 8,193 cannot be a subset of this set. And let's see, 1,999, compare that with the set of all x such that x is equal to 2n minus 7. N is the set of natural numbers here. All right, let's think about this. If I set 2n minus 7 equaling to 1,999, well, guess what? If I solve for n at 7, this will be 2n equaling to 2,006. Divide both sides by 2. That means n is equal to 1,003. So for n being 1,003, this will be 2,006 minus 7, which would give me 1,999. So 1,999 would be an element of this set. And then x compared with the set of all x such that x is equal to 2 to the n, and n is an element of the set of natural numbers. In this case here, we can say this will not happen. The reason for that, 2 to whatever n is, that's going to end up being some even number. And in this case here, I'm not going to be able to find anything where 2 to the n is equal to that, because I don't know what x is. So that would not be an element of this set. Because here, think of this, x can be an odd number or an even number. And an odd number would not be an element of this, where, of course, 2 to the n will always give me an even number. Because 2 to the first would be 2, or 2 to the third would be 8, okay? So here's where we get a counter example, like x equal 1. So that means x has to be in this, where x is equal to 2 to the n power. Okay. All right, now let's look at inequalities. That's an application of set concepts here. Let's say A and B are finite sets. So if A is equal to B, then the number of elements in A and the number of elements in B, well, if A is equal to B, then the number of elements in A is equal to the number of elements in B. And A and B are equivalent. That means it is possible to establish a one-to-one correspondence between A and B. And if A is a proper subset of B, then the number of elements in A must be less than the number of elements in B. and it is not possible to establish a one-to-one correspondence between A and B. Okay. So now let's look at some of these properties here. Well, some of the situations here for the number of subsets of a finite set. Let's say here, if P is a set with only the element A, then guess what? P has only two subsets, the empty set and set with the element A. But if Q has the elements A and B, we have four subsets. The empty set, set A, set with B, and the set with A and B. Now, what about R with three elements, A, B, and C? Here we're going to have 8 subsets. The empty set, set with A, the set with B, the set with C, the set with AB, the set with AC, the set with BC, and the set with A, B, and C. So if we were to generalize this, and you can pretty much figure out that there is going to be a pattern here. If there are n elements in a set, then 2 to the n subsets can be formed. So that means we can take whatever 2, and then what the number of elements, n, so it'd be 2 to the n power. So let's say there were 4 elements. The number of subsets will be 2 to the 4th, or 16. So in this homework example, let's say we let A equal the set with the elements 13, 14, 15, 16, 17, and 18. And in this case, if we want to find how many proper subsets or how many sets does A have? How many sets does A have? What subsets does this set A have? So here we use 2 to the n. And now we want to find out how many elements are there in A. So we count those up. There are 6 elements in set A. So the number of subsets will be 2 to the 6th, which will be 64. And now part B is how many proper subsets does set A have? Well, the number of proper subsets is going to be this, 2 to the n minus 1. So the number of proper subsets will be 1 less than 2 to the n. And we've already found out what 2 to the n was. There's 6 elements, so that's 2 to the 6th minus 1. And 2 to the 6th was 64. Subtract 1 from 64, you'll get 63. So there'll be 63 proper subsets for A. Okay, so that will conclude this video on section 2.2 dealing with describing sets. Do feel free to email me if you have any questions about anything that's presented in this video or any of the homework problems that are in my math lab.